So with regards to escalators, we conducted a series of simplistic evacuation scenarios whereby we had 400 agents, a single escalator and 2 stairs linking to an upper level, and we ran a series of scenarios looking at the different modelling methods and also how different operational strategies were influenced by different types of agent behaviour. And the list of scenarios, there were 7 scenarios, and we can see them listed here from S1 to S7. With regards to modelling lifts, we examined a series of 11 high-rise building evacuation strategies, and these explored the impact of the number of lifts on the evacuation time, the lift shuttle strategies, zonal strategies, and sky lobby strategies. The demonstration building we used for these simulations was 50 floors high, with 7,840 agents. This is 160 agents per floor above ground. There were 4 lift banks, each containing 8 lift cars. So there were 32 lifts in total. Each lift could contain 32 agents. Here we can see a pictorial diagram of the building, the 3D representation on the right, and on the left we can see the typical imprint of an example floor. There were stairs associated next to each lift bank. Okay, so we ran the simulations using our simplistic agent model, and the first scenario we ran was using stairs only, and this is what would typically happen in a normal evacuation. You'd only be allowed to use the stairs, and we did this so that we could compare our lift evacuations scenarios with this as a base case to see if there was any improvement. After the stair scenario, the first 4 simulations looked at the frequency of different lifts being available and how this impacted upon the evacuation, gradually incrementing an extra lift bank with each scenario. The next scenarios we looked at using a combination of both lifts and stairs to evacuate different sections of the building in different ways. And again, we looked at the concepts of zoning and also sky lobbies in this. Here is an example of the 32 lift top-down evacuation strategy, and if we remember, this is using the simplistic agent model so that all agents will elect to use their closest lift bank, and they'll wait for as long as needed before the lifts service their floor. So people are first of all evacuated at the top, and then the lifts gradually progress down onto the lower floors, and they're shuttled to the ground floor where people evacuate and go to the exits. So in addition to simulation modelling, we're also interested in finding out optimal lift evacuation strategies and developing some simplistic analytical techniques which could perhaps be used to assist the simulation process in finding our best evacuation or fastest evacuation strategy. So one evacuation strategy we're quite interested in is one where the bottom part of the building will use the stairs. Everyone in the bottom part of the building will use the stairs, and everyone in the upper part of the building would use the lift in a top-down manner. And what we came up with was TE, which is the time to evacuate the lift part of the building, and we also came up with TS, which is the time to evacuate the stair part of the building. And what we want to do is find out what value of E, and this is our boundary floor, where everybody above this floor will use the lift and everybody including and below that will use the stairs. We want to find out a value for floor E where the time to evacuate the stair section of the building equals the time to evacuate the lift section of the building. So we can solve for the equations below for E. And actually we can do this. We can actually put it into a form of a quadratic and solve it accordingly. The formulas assume that the same number of people on each floor, and it assumes that all lifts are fully utilised and service all floors. So how can this be used? Well, it can be used to reduce the simulation time. If you're running a simulation, you want to find the fastest evacuation time using this strategy. You can perhaps use this analytical technique to find it. It can also be used if you don't have access to evacuation simulations. by fire safety engineers as a hand-based calculation. So using the same principles, we decided to look at a slightly different strategy whereby we'd have 3 sections in a building and use the concepts of sky lobbies. So the stair part of the the lower part of the building will use the stairs, the middle part would use lift group 1, and the upper part of the building would use lift group 2. And in these scenarios, people who'd use a lift would initially walk down the stairs, where they would walk down to a sky lobby, then take the lift to shuttle to the ground floor where they would exit. And we use a similar sort of principle here to the other strategy, whereby we have the time to evacuate lift group 2 and the time to evacuate lift group 1 and the time to evacuate the stairs are all equivalent. And we want to try and solve this simultaneous equation. And from the equation, we want to basically solve for floors E0 and E1. These are our sky lobbies. And we can actually do that using the following two simultaneous equations. Basically, we've got the time, in equation 1, we've got the time to evacuate the stair part of the building is equal to the time to evacuate the middle part of the building. We can divide both sides by A and we get divide both sides by E0 and we get A equals and the rest of the equation. In equation 2, we have the time to evacuate the stairs is equal to the time to evacuate the top part of the building. And we can divide through by A to get E0 equals. And then we can substitute this back into the first equation to get the equation at the very bottom of the slide here. And in this equation we only have one unknown variable, which is E1. We can iteratively solve for this between values 0 and f, and that will give us our value for E1. We can then substitute it into the original formula to get values for E0, or get a value for E0. So we can actually solve this and find out the best floors to put our sky lobbies on, such that we can get the fastest evacuation time. Again, this assumes enough people arrive in the lift lobbies to fill up all available lifts when they arrive at the destination. To summarise the completed work, I've collected data, human factors data, on how people would behave on and around escalators and lifts via video footage and online survey data. We've quantified various types of human behaviour on these devices, and we've developed models within Building Exodus to represent the types of behaviour. We've explored a variety of different operational strategies and how they would be influenced by different human factors. We've also developed algebraic methods to assist in the simulation process to find efficient operating evacuation procedures for these devices. In this talk, I've only given a very brief overview of the work we've been doing. If you're at all interested in finding out some of the results of the data we've collected or the simulations we've run, here is a list of publications which have come from the work we've been doing. We expect there to be more in the future, but if you do require any further information, you can contact either myself or my supervisors. Thank you very much.